All right, good afternoon. So welcome to week 6. This is about our halfway point for the quarter. So let's see. I want to talk a little bit about the midterm. I want to take questions on the homework, mostly on the new homework that was posted over the weekend. And I'll grade the homeworks you turned in and get those back to you by Wednesday, and we can talk about those on Wednesday. So let me start by talking about the midterm. I already posted all of this in an announcement, but I'll go through it here just for emphasis. So your exam is this Friday. I'm going to start it at 12:15. That'll give a chance for people to come in late because... Awkward. All right, thank you. All right, I'm unmuted. So, all right, I want to talk about the midterm. I want to talk about questions on the new homework, and then Wednesday we'll talk about the homework that you already turned in once I've graded it and given you feedback on Canvas. So let me start with the midterm. So midterm will be Friday. I'm going to start it at 12:15, okay, because about a third of the class seems to come in 10 minutes in or so, and I want everybody to have the full time for it. So we'll start the exam at 12:15, which means the first 15 minutes we can hang out, you can ask last minute questions or whatever else. Exam will start at 12:15. I want you to consider it a 1-hour exam. Okay, 60 minutes. I will set up Canvas so that it actually closes after 65 minutes. Okay, but don't take it as a 65-minute exam. Try to do it in 60 minutes. And if you lose track of time or something, or you run into network issues and it takes, longer to submit your test or something, you've got a 5-minute buffer there. Okay? But please, 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 please do not wait until 64 minutes and 45 seconds to hit the submit button. Okay? And I'm going through this because we did online exams for 224 on Friday, and logistically it was a bit of a disaster. So people came in late, people didn't show up at all, people submitted after the timer expired and they didn't get their questions in. For a single exam, none of those things are insurmountable, but for an entire classroom of students, right, if I've got to get people emailing me questions, or I've got to monitor when people started and stuff like that, it gets complex really quickly. So so this is your fair warning, okay? The exam will start at 12:15. Plan on being online well enough before that so that if you have trouble getting connected or something like that, right, you're ready to go at 12:15. It's going to be a Canvas quiz. It's on Friday. It runs from 12:15 to 1:15. You can't take it any time during the day that you want. It's only offered during those times. Think of it as coming into the classroom and sitting down, and at 12:15 I hand out the exam, and at 1:15 I collect it. And if you don't hand me your paper, I walk out of the room and you've got a 0. Okay? So it's a Canvas quiz. It's online. 60 minutes. Make sure you submit it before the timer expires. And when you submit it, you'll get a grade of 0 automatically, right? Because I have to grade them. And Canvas will say, well, you haven't been given any points, and so you'll see a 0 out of 100, right? That just means I haven't graded it. Okay, if you actually manage to get a 0 on the exam, you're going to get a lot of feedback in the comments. So if you see a 0, don't worry about it. Okay, that just means it hasn't been graded yet. There'll be an honor statement in the beginning, which you'll need to read and agree to, and then fill in your name to say that you agree to it. And the honor statement basically says, this exam is open book, open note, but that's it. You're not allowed to use any other resources. You're not allowed to use Google. You're not allowed to chat with other people, etc., etc. Okay. And it will cover everything up through and including number theory. And it will be similar to what you've been doing in homework questions. So hopefully short questions or proofs that that you'll write up. And I'm going to suggest that you type these things in. Don't try to write things out by hand and scan them and then submit those. That's going to be way more trouble than it's worth. Just write these things up neatly. And if you need to do something like, you know, say for all, you can spell out for all, or you can say, you know, the letter A means for all, or something like that. Okay? But everything should be stuff that you can do by typing up. I don't want you to spend a huge amount of time trying to format what you're typing. Just put stuff in a way that's logically ordered so that I can follow what you're doing. All right. Any questions about any of that? All right. So that's all midterm stuff. That's Friday. Questions on the homework that just got posted? Yeah, can you go over the methods used to do questions 3 and 4? Sure thing, as soon as I figure out what questions 3 and 4 are. So, let's see. Question 3, write the following numbers as a product of prime powers. And question 4, use Euclid's algorithm to find, not ND, the GCD of the following pairs. Let me hop back onto Canvas. So factoring into prime powers. Well, this is just about factoring numbers. So how do you factor a number? Well, take the number in a calculator and go to town. Start trying to divide it. So a number like 25, right? A number that ends in 5 or 0 is divisible by 5. Right? A number that ends in 0 is divisible by 10. A number that ends in 4 is divisible by 2. So start dividing down by things, get smaller numbers, and that will get you to eventually to a bunch of primes. I'm assuming this was a question on homework 6. Yeah. And so just play around with those numbers, and you'll see some tricks along the way for when something's divisible by something. All right, question 4, Euclid's algorithm. So did you have a question about Euclid's algorithm in general? Or do you want to just run through another example of it? I'm fixing a typo where I said ND instead of find. All right, let's just do a quick run through on Euclid's algorithm. And somebody actually posted code for it on Discord, which is cool. So greatest common divisor. So I'll tag this. So Euclid's algorithm is a way to find the greatest common divisor of two numbers. So I don't know, I'm never good at figuring out good test cases. Let me run up something on the side here. So let's do the GCD of 140 and 35. Oh, that's going to be kind of uninteresting. So what do? We write the larger number as something times a smaller number plus something left over. So I'm going to go to my pocket calculator. 140 divided by 30. Yeah, that's an uninteresting example. Let's do 36. Okay, so GCD of 140 and 36. So write 140 as something times 36 plus something. So 36 will go in 3 times, and it will leave me 32 left over. And then bring these down. write 36 as something times 32 plus something left over. Well, 32 goes in once with 4 left over. And then bring these down, right? 32 is something times 4 plus something left over. Well, 4 goes in 8 times with 0 left over. Once you get to a 0, there's your GCD. Alright, so that's just a algorithm for finding those. And as a check, right, do 140 divided by 4, and I think that's 35. And do 36 divided by 4, and that's 9. So we know that this is a common factor of both of those. So that's one part of our test, right? Make sure it's a factor, because if we come up with 17, and 17 doesn't divide these, we did something wrong. So make sure that the greatest common divisor you come up with is in fact a divisor of both of those. And then how do you know it's the greatest one? Well, if you divide that out, you should find that the GCD of these should be equal to 1. And one way to tell that is to write these things as products of primes, right? So 35 is 5 times 7. 9 is 3 times 3. Well, there's no prime factors in common, so there can't be any factors at all in common other than 1. And after you run through Euclid's a few times, you get the hang of it, and then you don't have to really think too hard about the steps. So you've got 1, 2, 3, 4, 5 pairs of numbers to work on for the homework, so that should get you plenty of practice. 4B on the homework. Are we going back to the homework that was already done? The homework you just turned in. So translate the following statement into logical notation using quantifiers, where m of xy is the proposition that x is the mother of y. So this is a funny question to think about. So m of xy be the proposition x is the mother of y. Alright, so it's a family of propositions. And in 4b, we're asked to write a statement that says everyone, a proposition that says everyone has a grandmother. All right. Well, how would we write that everyone has a mother? M of xy is the proposition that x is the mother of y. So everyone has a mother. Well, if we think about it in the language of this proposition, right, saying everyone has a mother says that for every person there is somebody who is that person's mother. Right? For every person there is somebody who is that person's mother. So we could say for all y there exists an x such that m of x comma y. And we don't have to use x, y. Let's use differently chosen letters. For all people p, there exists a person m such that m is the mother of that person. Because with quantifiers, these letters are just placeholders, right? So this says that person P has a mother. To say that person P has a grandmother, we have to say that that person's mother also has a mother. So for all P, there exists an M such that M is the mother of P. And there exists a G such that G is the mother of M. So this is like some kind of combined quantifier. For all p, there exists an m such that this, and there exists a g such as this. And we might write that differently as for all p, there exists a g such that there exists a g and there exists a p, m, such that g is the mother of m and m is the mother of the person. So for all p in the universe, there exists a g and there exists an m such that g is the mother of m and m is the mother of p. So that would work and would be a little more usual notation than this, but they mean the same thing. All right, does that help? And like I say, I'll grade these over the next few days, give you feedback, and then we'll talk about them in detail on Wednesday. All right, anything else? All right, so let's talk about more induction. We started mathematical induction on Monday. We went through the definition of it in a rigorous sense. We went through kind of a hand-wavy informal definition. We looked at it with respect to climbing a ladder. We talked a little bit about why it works, and that got us a little bit into axioms, and the axiom of a least member in a set of positive integers. And then we started using this to prove some things. And so we proved a statement about the sum of consecutive integers and showed that a formula we used for finding the sum of consecutive integers in fact works. And I think we ended by adding up powers of 2 and show that the sum of consecutive powers of 2 gives you 2 to the next power minus 1. So we can prove all kinds of things with induction. Let's do a mathematical proof of a different type. Let's prove that n cubed minus n is divisible by 3. For all n bigger than or equal to 0. So as I said, on the midterm, if you want to write quantifiers, you can say for all or there exists. Or, you know, if you're not using an uppercase E somewhere, you can say the letter E means there exists and then use the letter E or things like that. I'm not going to hold you to some particular way of typesetting this stuff. Just make it clear to me when I'm reading this what you're doing, keeping in mind that, you know, I'll be reading these things for, you know, 10 or 15 hours. So try to make it pretty obvious what's going on. And just, you know, spell it out. If you're using the letter U to mean the union, you know, just say U equals union, something like that. All right, so let's use mathematical induction to prove that n cubed minus n is divisible by 3 for all integers n bigger than or equal to 0. So let's prove this using mathematical induction. Now we can use number theory to prove this. We can use modular arithmetic to prove this, and we'll do that afterwards, just to kind of see a different style of proof. But let's do this using induction. Okay. So let's start with a proposition. So let P of n be the proposition n cubed minus n is divisible by 3. Okay, let me make an important note here. This is not a hard and fast rule. This is just kind of what we're going to notice, is that in general, when we write a family of propositions, we're not going to end up including quantifiers. We could, okay? But in this case, P of n is the proposition that n cubed minus n is divisible by 3. Suppose I wrote this. So this is not what we want to write. Let P of n be the proposition n cubed minus n is divisible by 3 for all n bigger than or equal to 0. That doesn't really make sense, because P of 5 would be the proposition that 5 cubed minus 5 is divisible by 3 for all 5 bigger than or equal to 0. And that all 5 bigger than or equal to 0 doesn't really make sense. Maybe in a court of law you could argue that it's reasonable. But P of n is a proposition about a number n. It's saying that for this given n, this is divisible by 3. There's really no place for that quantifier. All right? Or saying that P of n is the proposition that, there exists something. Well, if n is 5, you can't say there exists a 5 such that, right? So in this case, even though the thing we're trying to prove is something about all n, right, the proposition itself is going to be about a particular n. So I'm going to let P of n be the proposition that n cubed minus n is divisible by 3. But now I can say, what do we want to prove? We want to prove P of n for all n bigger than or equal to 0. That's where the quantifier goes. Right? The thing we're trying to prove in the whole problem is P of n for all n bigger than or equal to 0. All right. So in order to prove this using mathematical induction, we need to do two things. One, we need to prove P of 0, and two, we need to prove P of n implies P of n plus 1, where n is some number bigger than or equal to 0. In other words, we have to prove a base case, and we have to prove the inductive step. All right, so step 1, prove P of 0. Well, P of 0 says 0 cubed minus 0 is divisible by 3. Well, we can prove that pretty easily because 0 cubed minus 0 equals 0, and 3 does divide 0. How do we know that? Because we can write 0 as some integer times 3. So P of 0 is true. And typically proving the base case is just a demonstration, because we're not talking about an infinite number of things to prove. We're talking about one thing, just this proposition when n equals 3. So then we go on to the inductive step. So this is step 2. Prove P of n implies P of n plus 1. Okay, step 1, P of n, y, hypothesis. Step 2, n cubed minus n is divisible by 3. Why? That's the definition of P of n. So 3 divides n cubed minus n. And we can write that because we assumed p of n. Okay, step 3, who the heck knows? I don't know. Let's think out loud. What do we want to show? We want to show that 3 divides n plus 1 cubed minus n plus 1. Why do we want to show that? Because that's what p of n plus 1 says, and what we're trying to do is prove p of n plus 1. So just look at your definition of the proposition. P of n plus 1 would be the proposition n plus 1 cubed minus n plus 1 is divisible by 3. So we want to show that 3 goes into this expression. Well, let's do some algebra and figure out what this is equal to. This is n cubed plus 3n squared plus 3n plus 1. We'll figure out how to do that quickly in our heads at the end of the course. If you don't already know it, we'll use the binomial theorem. And then we're going to subtract n plus 1. So this is n cubed plus 3n squared. 3n minus n will be 2n, and 1 minus 1 will be 0. That doesn't feel right, but that's okay. And so we want to show that 3 divides this thing. And all we know is that 3 divides n cubed minus n. So this is that piece of the proof where we have to kind of scratch our heads and sit back and, you know, sip on a Coca-Cola or whatever, and look for inspiration. And the possible inspiration here is, well, we're trying to show that this is divisible by 3. I don't have to worry about this. I know 3n squared is divisible by 3 because it's 3 times n squared. So if I can show that n cubed plus 2n is divisible by 3, then I'm done. If I know this is divisible by 3, then I can add something divisible by 3 and get something divisible by 3, and since that's going to be equal to this, I'll be done. I have to make it very formal, but on this intuitive hunt, my question is, can I show that n cubed plus 2n is divisible by 3? And at first glance, no, but we know the following. We know that 3 divides n cubed minus n. Why do we know that? Because we're assuming p of n. Well, you know, if this was plus 2n, that would be great, but it's actually minus 1n. But is there some way to get from here to there? Any ideas? Well, lots of ideas. If we were to add 3n, this expression becomes that expression. And guess what? 3n is divisible by 3. So we know this is true, so 3 also divides 3n. Therefore, 3 divides n cubed minus n plus 3n, which is equal to n cubed plus 2n, which is that. Perfect. Awesome. All right. Now, if you turn this in, right, that gets the frowny face on the test. That is not a proof. That is a stream of consciousness. Okay? That's the magic. That's the insight, right? So that's the good stuff. But to write a formal proof, you need to take that insight and put it into this very rigorous structure so that somebody who doesn't have that insight will get it from reading your proof. All right? So now we take what we did here and we formalize it. And yeah, we know 3 divides 3n because what does it mean to say something's divisible by 3? It means it can be written as 3 times an integer. And 3n is 3 times an integer. It's 3 times n. Because n is an integer, which we didn't say, but we're still in that mindset where all of our n's are ints. All right, so how do we bundle this up? Well, it can take a few tries, and I would recommend, pencil and paper with a really good eraser, or a chalkboard or whiteboard. But we can just kind of go backwards, and there doesn't have to be a clear reason why you're going from one step to another, as long as you explain why that statement is true. You don't have to justify why you're doing it. Right? You might have gotten it from reading your tea leaves. That's okay. As long as we have an explanation for why each statement is true. So I'm going to do the following. I'm going to say n cubed minus n equals 3 times k, where k is an integer. So maybe there exists a case such that n cubed minus n equals 3k. That's the definition of divisibility. All right, so I'm going to do n cubed minus n plus 3n equals 3k plus 3n equals 3 times k plus n. That's just algebraic manipulation. Yeah, or some other kind of leaves. And this over here is n cubed plus 2n equals 3 times k plus n, which I'm just going to write as 3 times k1, where k1 is an integer. And why did I want to do that? Because then I could add 3n squared. So n cubed plus 3n squared plus 2n equals 3 times k1 plus n squared. Right, so I just factored that 3n squared into here, equals 3 times k2, where k2 is an integer. And why did I want to do that? Because I wanted to rewrite this as this. So n plus 1 cubed minus n plus 1 equals, and go through this manipulation, n cubed plus 3n squared plus 3n plus 1 minus n minus 1 equals n cubed plus 3n squared plus 2n, which is this thing, so that's equal to 3 times k2, and that's all, glorious algebra. And therefore, since this is written as 3 times an integer, 3 divides n plus 1 cubed minus n plus 1, and that's the definition of divisibility. And that's the statement of Pn plus 1. Therefore, starting with P of n, we concluded P of n plus 1. And then you need to do the grand finale, which says, therefore, P of n for all n bigger than or equal to 0. And the reason for that is mathematical induction. And that's the actual end of your proof. So the proof is kind of, looks kind of complex and befuddling maybe. But it's really, some insight over here that we can ignore that 3n squared. And the real insight is, if you add 3n to this, you get that, right? But now somebody who believes in propositional logic and algebra and mathematical induction can simply go through step by step. Yeah. Okay, yeah, I guess that's true, right? And they don't need to have that insight. And in fact, a lot of times when you read proofs, you don't really come away with an intuition for why it's true, but nonetheless, the proof will convince you that the statement is, in fact, correct. All right, so that's a proof involving divisibility. If we wanted to prove that same statement without using induction, if we wanted to use number theory, so use modular arithmetic to prove 3 divides n cubed minus n for all n bigger than or equal to 0. Well, what does it mean to say that a number is divisible by 3? How can we express that fact using something from modular arithmetic? So 3 divides x is the same as what? So throw something in chat if you got an idea. Yeah, x is congruent to 0 mod 3, exactly. Because saying this means that when you take x and divide by 3, you have a remainder of 0. Well, if you divide with a remainder of 0, it means that this thing divides it perfectly, which is the same thing as saying 3 divides x. So we can reduce this problem to the following. Show n cubed minus n is congruent to 0 mod 3 for all n bigger than or equal to 0. Well, one way to do this would be to show this for n equals 0, 1, 2, 3, 4, 5, 6, 7, a million, a billion, a skrillion, and do that for all possible integers, right? Infinitely long proof, but theoretically you could do that. But remember, the cool thing about working with modular arithmetic is we can constantly reduce things, modulo whatever our moduli is, anytime that we want. So we could calculate n cubed minus n and then find what it's congruent to mod 3. Or we could take n cubed, reduce that mod 3, and then subtract n and reduce that mod 3. Right? Or we could reduce n mod 3 to begin with. And that's a really interesting option, because if I reduce n mod 3, how many different answers can I come up with? 3. Any integer I pick is going to be congruent to either 0, 1, or 2. So I don't have to test this equality for an infinite number of values of n. I only have 3 cases. Case 1, n is congruent to 0 mod 3. Well, then n cubed minus n is going to be congruent to 0 cubed minus 0, which is just 0. And that's not surprising. If n is divisible by 3, we kind of know n cubed is divisible by 3 and n is divisible by 3, so their difference is divisible by 3. Okay, this is using modular arithmetic. All right, this is the easy version of what we did a lot of work to show with even and odd numbers, when we were working through with the definitions of divisibility, or the definition of being odd or even. But with modular arithmetic, this becomes a lot simpler, right? If n is the multiple of 3, we know it's congruent to 0. N cubed minus n is congruent to 0 minus 0 is 0. Okay, case 2, n could be congruent to 1. in which case n cubed minus n is congruent to 1 cubed minus 1, which is 1 minus 1, which is congruent to 0. And again, the difference is divisible by 3. The only other possibility is n is congruent to 2. And n cubed minus n will be congruent to 2 cubed minus 2, which is congruent to 8 minus 2, which is congruent to 6, which is congruent to 0 mod 3. And those are the only 3 possible cases, so in all cases we've shown n cubed minus n is divisible by 3. You're done. So in these particular types of problems, right, we've got a pair of options. We can use mathematical induction, which can be a lot of algebra and a need for an insightful spark and then a lot of formalism. Or, you know, if we're allowed, we can simply go through all the possible situations for what n is congruent to mod 3, and, you know, it's half a page of work. Now, on tests, I would say explicitly, you know, do this using mathematical induction, or do this using modular arithmetic, or do this any way you want, but we get to the same place in the end. All right, let's change gears. Let's work on a different kind of problem. So I want you to imagine you have a kitchen floor. This is like the actual size of my kitchen now, which I'm told is not the smallest kitchen in the world, but it feels like it. So imagine you have a kitchen floor, and it's covered with tiles. And these tiles are all square. And the tiling has gotten very old and it's cracked, and you want to replace it yourself. Okay? So you go to Home Depot or Lowe's and you price out tiles, and tiles are really expensive, right? It's like going to be ridiculous to try to like get enough tiles to redo the floor. So you leave the store and you're kind of dejected and you're trying to figure out what to do, and someone says, "Come over here." And this person has a van and he's like, "Hey, I hear you're looking for tiles. I'll make you a good deal." And this person has, you know, a whole box of tiles to sell you, and will sell them to you really cheap, but they're kind of funny looking tiles. They're L-shaped. They look like this. And, you know, these squares are the same size as these squares, but you're not getting a box of individual squares that you just put down. You're getting these funny L-shaped pieces. But it's a really good price, right? So you're like, okay, I'll take those. So you go home, you'll go into your kitchen, and your task is to cover your floor with these L-shaped tiles, right? So maybe I'll take one of these L-shaped pieces and I'll put it right here. And maybe I'll put another one right here. And I'll put another one right here. And, well, I got a problem because I can't get both of those, but maybe I'll put a plant over there or something, you know. And you can try different tilings and see, you know, can I cover my floor perfectly with these L-shaped tiles? Yeah, Tetris. And, you know, you have to cover the entire floor. You're not allowed to have a tile sticking out of the side. You're not allowed to have open gaps here. You're not allowed to overlap your tiles. And you're not allowed to cut these L-shaped tiles because, you know, they always crack when you try to cut them. And so the question is, you know, can I actually cover my floor with these tiles? Yeah. All right, so let's analyze this question. And, you know, we can try different ways to cover this with these, and we can move them around. This didn't work out, but maybe if I had done something differently, maybe if I had turned this tile this way, so it would be too high and too high, right? Maybe that would work. So I'm going to give you a theorem. Okay. First, let me tell you when this will work. Okay. This would work if this was an 8 by 8 space of tiles that I needed to cover, and I had one square I didn't want to cover. So say I have a pipe coming out right here. So I don't want a tile over this spot, but I want every other spot covered. I can tile it, guaranteed. And if it's 16 by 16 or 32 by 32, or in general, if it's 2 to the n by 2 to the n with one missing spot, I can tile it perfectly with these L-shaped tiles. And there may be other shapes that work as well. But you're guaranteed if you have 2 to the n by 2 to the n tiles and you've got one spot that you don't want to cover, you can cover it with these. And we can prove that. Okay, so let's do an inductive proof of the tiling theorem. All right, so let P of n be the proposition a 2 to the n by 2 to the n floor with one missing tile can be covered perfectly with L-shaped pieces, with L-shaped tiles. All right, that's our proposition. And other than to 2 to the n over here in the multiplication, there's nothing mathematical in here, right? It's a very kind of conversational proposition, but nonetheless we can come at this with mathematical induction and prove this rigorously. And we want to prove P of n for all n bigger than or equal to, let's go bigger than or equal to 1. Because if n is 0, this would be a 1 by 1 floor, and we know we can't cover a 1 by 1 floor with an L-shaped tile because we'd have extra stuff. And if n is negative, this is like a fractional number of tiles. But for n bigger than or equal to 1, the claim is that we can prove P of n. Okay, well the claim is P of n is true. Okay, so let's prove this using mathematical induction. Step 1 is the base case. So we want to prove P of 1. Alright, well what does P of 1 say? It says a 2 by 2 floor with one missing tile can be covered. Well, it turns out if we have a 2 by 2 floor with a missing tile, the missing tile can be in one of 4 spots. It could be right here, could be there, could be there, could be there. Alright, if we're missing a tile up here in the upper left, we can use our L-shaped piece right there, and we're done. If we're missing our tile in the upper right, we can use our L-shaped piece in this orientation, and likewise for the lower left and for the lower right. So P of 1 is definitely true. If you have a 2 by 2 floor with one spot missing, we can cover it perfectly with one of these tiles. And we know that because there's your map. That's how you do it. Alright, I should have tagged this. So this is floor tiling. Alright, So, and this is going to be something much more than just knowing how to tile floors when we're done. This is going to be key to everything we do, so bear with me. All right, so we need to do the inductive step. So we need to prove Pn implies Pn plus 1. All right, that's our last remaining goal, to prove P of n for all n bigger than or equal to 1. All right. How the heck do we do that? Well, we're not going to use algebra this time. Okay, we're going to use something else. So step 1, P of n, and I'm not going to write this fully as a formal proof because I could just keep adding more and more words and it would look formal, but let's just look at this kind of intuitively, okay? Step 1 is going to be P of n, that's our hypothesis, okay? What does this mean? This means 2 to the n by 2 to the n minus 1 tile can be covered perfectly. We just want to remember that definition. Okay, so we're assuming a 2 to the n by 2 to the n floor can be covered perfectly, as long as there's one missing tile. Okay, so how do we do P of n plus 1? Let's imagine our floor. And let's suppose there's 2 to the n plus 1 tiles across. And there's 2 to the n plus 1 tiles up and down. Let's go ahead and split this room into 4 quadrants. And so each of these quadrants has a height of 2 to the n and a width of 2 to the n. Because 2 to the n plus 1 split in the middle, you get 2 to the n. Alright, we know P of n is true, which means that if there was one tile missing from here, I could cover this region perfectly with L-shaped tiles. Well, remember, there is one spot missing from somewhere in this 2 to the n plus 1 by 2 to the n plus 1. So let's just suppose that this tile right here is the tile from the entire floor that we don't want to cover. Well, given P of n, we know that this quadrant can be covered with L-shaped tiles, because it's a 2 to the n by 2 to the n room minus 1 tile. So we can cover this perfectly. Alright, we got a quarter of the room done. Unfortunately, this was the only spot with a missing tile, because the whole room only has one missing tile. And now we've got 2 to the n by 2 to the n regions that don't have any missing tiles. So here's what I'm going to do. I'm going to temporarily ignore one tile up here in the corner. And I'm going to cover everything in this bottom left region except for that one corner tile. And then I'm going to come over here and I'm going to ignore a corner tile. And since this is 2 to the n by 2 to the n minus 1, I know I can cover all of this stuff. And I'm going to ignore one more corner region right here. And that's going to let me cover all of this. And I'm almost done, except what's missing? These 3 tiles right here, which guess what? Are in the shape of one of our L-shaped tiles. We take one more tile, plunk it down right there, and we are done. And we've covered the entire 2 to the n plus 1 by 2 to the n plus 1 minus that one tile. And there's 3 other possibilities. That missing tile could have been over here, or over here, or over here. And we could repeat that thought exercise 3 more times for each of those cases. Or, you know, if you're mathematical-ish, you can say, without loss of generality, assume the missing tile is up here. Now that's a big stick that wields a lot of power and can easily be misused. But basically, when you say without loss of generality, you're saying there's nothing about choosing this versus that or that or that changes anything in the proof except details. But either way, you do this or justify this in all four cases, and you've shown that no matter where that missing tile is, you can cover the remaining regions with L-shaped pieces, right? Therefore, P of n plus 1. And now you just do the same old thing. P of n implies P of n plus 1. Therefore, P of n for all n bigger than or equal to 1. And that's mathematical induction. And that's the end of your proof. All right, what do you think about that? Funny, quirky, cool, weird, annoying, reasonable? I think it is pretty cool too. It kind of comes out of nowhere, right? It's even more subtle than, you know, the sum of integers proof or the sum of powers of 2. But it follows the rules of logic and mathematical induction. We have to accept this as being true. And it is a valid proof, and we would have to do some, you know, a lot of fancy legwork to really make this truly rigorous, like a mathematical proof. We'd have to define what exactly a tiling looks like and all of this stuff. But intuitively, right, we can see it, and it's the intuitive part I'm interested in because of what this means for us. Okay, so so let's go back to our story. Suppose you got, you know, this huge supply of L-shaped tiles from this person in the parking lot at Home Depot. So you've got this massive supply that was like almost completely free to you, and you decide you're going to go into the floor tiling business, right? So you're going to advertise, you know, got a 2 to the n by 2 to the n floor with a missing tile. I'll tile it at half the price of the other people. And this is your business, right? You're going to go in, you're going to tile floors. Well, you know, what we did was we proved that you can tile, but if your job was actually, you know, here's a room that's 1024 by 1024, and here's one missing square, go ahead and tile it. Could we actually do that? I mean, we have to believe that it's doable because we've done a proof, but how would you actually do it? And here's an idea, and this is going to be probably the key idea from this course, and it's going to be one of the key ideas in CSE215. Okay, so I'll just call this the key idea. So the idea here is outsourcing. All right. You want to cover this person's 1024 by 1024 room. All right. So you drive over, you've got your mask on, you've got your big box of tiles, you walk into this person's house, and there's their massive kitchen. And it's 1024 by 1024. That's 2 to the 10th. And, you know, they've got the one pipe coming up from the ground right here. And they're like, oh, but we don't want you to cover that spot with a tile. And you're like, okay, no problem. I won't even charge you extra. All right, how are you going to start laying down tiles here? The answer is you don't. Here's what you do. You take this large room and you split it into 4 quadrants, where each of these is 512 by 512. Well, you have a friend who also took this course with you and also got a box of L-shaped tiles, and they're also willing to tile people's floors, but they'll only go up to 512 by 512. They won't do the 1024 size, right? So you call your friend over and you say, hey, can you tile this floor for me? I'll give you, you know, a few bucks. And they say, sure, and they tile this section of the floor for you. Okay. And then you knock out this corner and say, hey, I got another job. Can you tile this floor for me? And they say, sure, and they tile it. And then you knock out this corner and say, you got another job. Can you tile this for me? And they say, sure. And then you knock out this corner and say, I got one more job for you. Can you tile this floor for me? And they say, yeah. And you pay them for their work and they leave. And then you take your pile and you pop it down here. And you report to the owner of this kitchen, hey, your floor is done. And you get paid for that. Hopefully more than what you paid to get those 4 sections tiled. And I don't need to be any smarter than that. I don't need to know, the secret skills of tiling floors with L-shaped tiles. All I need is a friend who knows how to do up to room size 512, and I can do my 1024 room. Right? And my task is really simple. Just outsource, 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 put down 1 tile. All right, well, your friend, they have a harder job. Your friend has to actually tile a room that's 512 by 512. So they're going to come along and they're going to see this 512 by 512 room. And it might, have a tile missing from the corner, or it might have been a tile missing from down here. But, somewhere there's a tile missing, and they need to cover this with L-shaped tiles. Well, what do? They outsource to another friend. And that friend can handle rooms that are 256 by 256. So they say, hey, I got 4 jobs for you. First tile this room, and then this one, and then this one, and then this one. And after those 4 are done, they pop a tile in here, and bingo, they've tiled a 512 by 512. If you have enough friends, this will work all the way down to the person who's hired to tile the 2 by 2 with 1 missing tile. And they don't have to outsource to anybody. They have a map for how to tile that 2 by 2 room. If that one's missing, I'll put a tile there. If that one's missing, I'll put a tile there. So think about this, okay? Think about how this would actually work. You got a bunch of friends with bunches of tiles and a lot of time and patience, and if you're hired to do this 1024 by 1024 room, as long as you can call on your friend and say, hey, I'll be back tomorrow, please tile these 4 regions for me. They do the work, you come back, you place 1 tile, and you're done. You've covered the whole 1,000,000 square room. And the person who does the 512 by 512, they don't have to do any work either. They hire someone to do these 4 quadrants, and they place 1 tile. And the person who does the 256 by 256, they don't have to do any work. They hire someone to do 4 128 by 128 rooms, and they place 1 tile. Nobody is ever actually doing any work except the person who's doing the 2 by 2 floor at the end. And they don't actually have to be very, very clever. They just have to follow one of these 4 pictures. Okay, this is going to be the key to CSE222 and to most of what we do in computer science. Is basically finding a friend to do all the work for you. You take the work that your friend or friends have done and put it together to get, a very clever solution without doing a lot of work. Yeah, it is kind of pyramid scheme-ish. But it's okay, because in the end, this friend who is doing this work, and this friend who is doing this work, and the friend who is doing the original work, they're all you. In the end, you're going to be the person who's doing all of this work. Or in 222, your program is going to be the thing that's doing all of this work. So you're going to change hats. You're going to say, I'm Mr. or Mrs. 1024 by 1024, and I'm going to tile this room. Well, you don't actually call up a friend and say, can you do the 512 by 512? You switch hats. And I says, I'm the 512 expert. and you outsource this subtask to yourself. Well, how do you do that? Well, you put on your 256 hat and you say, hey, tile this region for me, please. But I still don't need to know anything until I get down to the 2x2 case, and then I pull out my handy-dandy chart and I say, oh, you know, I'm the 2x2 expert. There's a missing tile here. Okay, I'll put an L-shaped tile there. I'm done. And I hand that to the 4x4 expert, and they put that together and build it into a 4x4 solution. So yeah, this is exactly finding a friend to do all the work for you. Okay, and this is what we call recursion. And I'm not really going to talk about recursion per se in this course, but we are, because mathematical induction and recursion are really the same thing. And this inductive step is about going from one case to another case. That's basically a recursive call. And the base case is where your recursion ends. I can't continually cut the kitchen space into 4 quadrants and ask somebody else to tile it, because when I get down to this final 2x2 case over here, right, I can't cut it down to a 1x1 and ask somebody to tile that. It doesn't work. You can't tile a 1x1 with an L-shaped tile. So this is where the buck stops, right? This is where you actually have to do some work. But at that point, the work is so simple that you can describe the complete solution with just a little 4-section answer guide. All right, so while we're thinking about that, let's try another example. And let me get a test case here. Let's see. So let's talk about postage stamp problems. So the general idea of a postage stamp problem is you're given an infinite supply of stamps with certain denominations, and your goal is to combine them in a way to make a certain exact postage. Okay, so you have certain denominations. There's no limit on how many stamps you have, but you want to combine them to make exact postage. And it's kind of like counting change with regular currency, right? How do you make 28 cents change when you have pennies, nickels, dimes, quarters? And can you always get an exact amount of currency? So if you have pennies, it's easy. You can always do, 28 pennies to get 28 cents. But if you have, a smaller mix of currency or postages available, can you make all possible amounts of postage or change? So let me dredge up a quick example. So bear with me 1 second. I'm just going to find an old example. All right, let's say you have 4 and 5 cent stamps. All right, and you want to make some postage. Some amount of postage n. Okay, so let P of n be the proposition that you can make n cents postage from 4 cent and 5-cent stamps. Some number of them. All right. Let's prove P of n for all n bigger than or equal to 12. All right. Using mathematical induction. So case 1 is a base case. Prove P of 12. Can you make 12 cents out of 4-cent and 5-cent stamps? Yeah. 12 is just equal to 3 times 4. So again, these won't be as rigorously mathematically precise as some of our other proofs, but the underlying logic is still very rigorous. Okay, P of 12 is true because you can demonstrate a way to make 12 cents postage out of 4-cent and 5-cent stamps. Take 3 4-cent stamps and you're done. Okay, so the inductive step says prove that if you can make n cents postage, you can make n plus 1 cents as long as n is bigger than or equal to 12. All right, there are two possibilities. All right, we know we can make n cents postage. That's our hypothesis. So, so find a combo of 4-cent and 5-cent stamps that add up to n. All right, P of n says we can do that. We can find a combination of 4-cent, 5-cent stamps that add up to n. So two possibilities. Possibility 1, that combo includes a 4-cent stamp. That's certainly a possibility, right? It may be that the way you made n cents postage included a 4-cent stamp. It might have been more than 1 4-cent, but it includes a 4-cent stamp. Well, if that combination of postage gets you n cents, if you replace that 4-cent with a 5-cent stamp, that new combination of postage will add up to n plus 1. And bingo, you've made n plus 1 cents postage using 4-cent and 5-cent stamps. So if you have a solution for n, and that solution includes a 4-cent stamp, just replace that 4-cent, any one of those 4-cent stamps with a 5-cent, and you've got a solution for n plus 1. But there's another possibility. Possibility 2, that combo does not include a 4-cent stamp. That's the other possibility. Well, if it does not include a 4-cent stamp, we can't replace a 4-cent with a 5-cent. But if it does not include a 4-cent stamp, then the combo has only 5-cent stamps. Well, how many 5-cent stamps? If it only had one 5-cent stamp, then n would have been 5. And we need n to be at least 12. If the combo had only 2 5-cent stamps, then the postage from that would have been 10. And we're only considering n bigger than or equal to 12. So if the combo has only 5-cent stamps, it must have at least 3 5-cent stamps. That's because n is bigger than or equal to 12. Well, if you have 3 5-cent stamps, replace those with 4 4-cent stamps. So the second case, we're guaranteed there's at least 5-cent stamps in this combo that added up to n. If we take those 3 5-cents, peel them off the package and replace it with 4 cents, what's happened? We took off 15 cents postage, we added 16 cents postage. Our total postage has gone up by 1. Our postage was N, now our postage is N plus 1. And so again, in this case, we can find a combo of stamps that adds up to N plus 1. And those are the only two possibilities. Either the combo for N had a 4-cent stamp or did not have a 4-cent stamp. And in either case, we can describe how to get a combination that adds up to N plus 1, and therefore P of N plus 1 is true. So that proves P of N implies P of N plus 1 together with our base case. That tells us P of N is true for all N bigger than or equal to 12. Alright, so we've proven that you can always make postage out of 4-cent and 5-cent stamps, but in proving this, we've actually come up with an algorithm for making postage. What's the algorithm? Someone comes in with a package and they need 86 cents postage, right? And my job is to figure out the combination of 4s and 5s that get up to 86. Well, I hand the package to a friend and I say, hey, can you put 85 cents postage on this? They say, sure thing. They put 85 cents on, I get it back. And now, if there's a 4 cent on there, I peel it off and put on a 5. If there's no 4 cents on there, I peel off 3 5s and put on 4 4s, and I've got 86 cents. Now, how did my friend make 85 cents postage? Well, they did the same thing. They handed it to another friend and said, can you put 84 cents postage on here? And then they got it back, and if there was a 4, they replaced it with a 5, and if there wasn't, they replaced 3 5s with 4 4s, and they changed the 84 cents postage into 85. And then they handed it to me, and then I did my thing to make 86 cents. And this goes back all the way until somebody hands them the package and says, hey, can you make 12 cents postage, please? And they say, yeah, I'll just do 3 4-cent stamps. And they don't need to turn to a friend to help with that. They have the explanation of how to do 12 cents postage right here. And you can code that up. Okay, we'll probably code that up on Wednesday just to see how this works. And so mathematical induction shows us how to prove some of these things, but a lot of times those inductive proofs have hidden in them the actual algorithms to solving a particular problem. On the other hand, sometimes when we come up with an algorithm that we think solves a problem, how do we prove that it actually solves the problem? Will come down to mathematical induction. And we'll basically prove that if this solves the problem for a certain case, it will solve it for a larger case. And we'll also prove that it works for some particular base case. So yeah, these things will play off each other in fairly glorious fashion in lots of different contexts. Alright, so that's a postage stamp problem. By the way, on YouTube, on the computer science, I don't know if it's on the computer science link, but if you go to my channel, one of the playlists is on mathematical induction, and we work through all of these things in careful detail. So it's another presentation. Some of these problems we haven't gone through yet, but there's a series of videos there that basically go through these ideas again. So that's another resource. All right, so where do we go from here? We'll play around with some more specific examples, adding up odd integers, for example. We can look at some inequalities, like for example, proving that that n is less than 2 to the n for n bigger than 0. Or proving that 2 to the n is smaller than n factorial for sufficiently large n. So we can look at inequalities like that. We can prove things about subsets, right? So we had this fact that the number of elements in the power set of S was equal to 2 raised to the number of elements in S for a finite set S. We can prove that using mathematical induction. So we'll play around with some more of these examples on Wednesday, and we'll talk about the homework that you just turned in. And we'll look at some other odd examples of induction, including the odd pi fight. And then we'll look at some possible errors that we can get into, things where mathematical induction may look like it's doing the right thing, but actually leads to a wrong result. And we'll see where that kind of thing can happen. And we'll probably look at some code for a stamp problem just to see. And we'll talk about towers of Hanoi. So lots of good stuff coming up on Wednesday. All right, we are out of time. I will see you next time. Have a good afternoon, and catch you later.